There we go. Hey, everybody. Welcome back. How are we doing this fine evening? We're in for round two. What's going on, Sahar? Good to see you. Welcome back. Hey, Mary, Jessica, what's going on? I do have to say, I know if you were here for the last class, I had my pen tool thing failing. I think I fixed it during the break. So I think we should be good, which is super helpful for Orgo because I got to draw a bunch of stuff. And so I was a little nervous about it not working for this class. But I think we'll be good. I'll let you know if it fails. And if so, then Liz is going to step in and draw a bunch of pictures for us, and it should be fine. Yeah, so there's a lot of stuff we covered today. There we go, all the red marks. It's still working. I'm very excited that it still works. I thought it was broken forever, but we'll see. All right, so yeah, we got a lot of stuff covering here. This is actually one of the brand new channel classes. I don't know if we've even run this one before, so welcome to the brand new digs. We go through a bunch of stuff today. It's pretty interesting, and we actually cover a lot of major concepts. The last thing we do is where we get into the more NMR, IR type stuff. But we talk about pretty much every single lab technique today. So we talk about chromatography, we talk about organic separations, talk about separatory funnels, polar, nonpolar, weak acids, strong bases, weak bases, all that kind of stuff for separation. We'll also get a little bit, not too much to be honest, because we get into this in other classes as well, but the bioorganic compounds by electrophoresis, like SDS Page versus native SDS, all that kind of stuff. And so electrophoresis, nucleic acid backbones and things like that. Anodes, cathodes, if you want to get crazy. So we will discuss that stuff. But we do then, mostly at the very end, get really into identifying functional groups using NMR and IR, and that'll be pretty much where it's really at in terms of the standard spectroscopy stuff. Yeah, seriously, agreed to Mary. Agreed to Mary. Usually these get made about 3 weeks before they go live, and so that's pretty much spot on. It was made in the end of April, March, so pretty fun stuff. All right, so let's talk about chromatography first. If we're going to do chromatography, what is generally the first type of chromatography that we learn about or do? TLC, you got it. Crazy, sexy, cool, right? No scrubs. You guys picking up what I'm putting down here? Maybe a little bit? A little bit? Yeah, Sarah knows what's up. It's a band from the 90s, right? TLC? I don't know. Okay. But so thin layer chromatography or a band from the 90s, whichever you want to call it. There we go. Alexander knows what's up. But so the main thing we do here is really relating to Rohini is also very excited about that reference. But so we talk about two main phases. Now this is true for TLC. This is true for column chromatography, gas. And also, just as a heads up, we're going to go through the gas and high pressure, high performance liquid chromatography. We're going to do that stuff super quickly. We're just going to give you the general idea. But this is the major concept that all of this stuff relates to. And if you get this down, honestly, just think of everything else as just another example of the same thing. So in all types of chromatography, we have two phases. We have a stationary phase, which in this case is our plate. Generally, it's a silica plate. And then, of course, we have our solvent. And our solvent tends to be fairly nonpolar, the mobile phase. So for TLC, the standard is, and I know you can change it and have different forms of TLC, but the big picture, most common one, is that you have a polar stationary phase and a nonpolar solvent. And so what we do is I should have totally, well, here we go. I was going to stick a napkin in my water to show how it works, but I don't want to put a dirty napkin in my water. But so generally speaking, if you were to take your water and stick a napkin in it, the water would climb up the napkin, defying the force of gravity, which is weird. So what is it that causes the water to climb up the napkin even though gravity's pulling water down? Nice, capillary action, exactly true. And so it's all due to capillary action. Basically, water is going to move up, and it's the same thing. Even if you put a nonpolar plate inside of a polar solvent, that nonpolar solvent is going to creep up the nonpolar plate due to capillary action, exactly. And we won't get into the physics of that. If you want to get really nerdy in the physics of it, hit us up in Q&A. We can get weird. But for the MCAT, that's basically all we need for that. And so the whole idea is that it's going to move up the mobile phase as it creeps up. So now before we actually have this run, what we'll effectively do is we're going to put our sample spots. Well, maybe we'll do it this way. I'll say that we drip this thing into a solvent. So I'll call this the solvent down here. And so then your solvent's going to start to creep all the way up to the top of the plate. And as it starts to climb up, we have these different types of samples. And these are the actual experimental samples that we care about that we put right at the bottom above the solute line. So now it looks like this sample traveled up to here, and we've got this, we'll make it a gray sample, only moved to about here. So what we're really doing is we compare how far the samples moved relative to the, do you guys know what this line's called? How far the solvent travels? It's called the solvent front. Oh, we'll get to RF in a second. So that's the retention factor. That'll be the next thing we do. So it's, you don't need, well, mostly just know it's the distance the solvent travels is one thing, and then we compare the distance the solvent travels, which is, you call it the solvent front. I don't know if you need to know that term, but what we're effectively doing is we're taking that distance that each sample travels, which in this case would be this distance right here, and we divide that distance by the solvent front. So in this example, notice we said that the solvent front was about 50 millimeters. The sample traveled 37. So then how would you solve for the retention factor of sample green? Perfect, Hannah. Just divide 37 by the solvent front. So 37 divided by 50. So, and one thing that already be, and we had a couple people switch it around and put the 50 over 37. What is the maximum RF value you will ever see? What's the maximum value? Just one, exactly. So do be aware of that. You're always putting the smaller number on top of the bigger number. The max is 1. You'll never be bigger than that. And so let's actually do a little quiz then. So what would we know about the sample if its RF value was 1? Like, what would it be property-wise? Exceptionally, it'd be on top, but tell me, there, that's what I'm getting at. It'd be very nonpolar. It's the same as the solvent, right? So it's basically the exact same polarity as the mobile phase. And so that's your solvent or the mobile phase. If it's RF1, it's identically the same as the solvent. And since the standard for TLC is that you use a nonpolar solvent or mobile phase and a polar stationary phase, generally it's a silica plate, that's why generally you'd say it's a very nonpolar if it goes all the way up to the top. I'm not sure about the molecular weight here. Yeah, I don't know if molecular weight's a big factor there, Esther. That's a really good question. What is the one tool that we do talk about molecular weight a lot? Because there is one type of lab technique that it's what it's all about. I don't think it might, but not that I'm aware of for this at least. Yeah, that's the electrophoresis, the SDS page specifically. You got it, totally true. The gel electrophoresis is all about size, totally, and specifically SDS page in the category of electrophoresis too. You got it. So yeah, that's the one more about mass. You could also do mass spectroscopy. We actually don't cover mass spec today. It's not that high yield of a concept, but it's, that's another one that does deal specifically with mass. You have, oh great, Gabriella's got another good one. Size exclusion chromatography is another one that separates according to size. Or I guess you could use mass for that as well. That's a very good point. So that is a specific type of column chromatography that also does it according to mass. I forgot about that one. That's a very good point. Cool, good point. All right, so there we said the RF value is 37 divided by 50. You could then, of course, then solve that for about 0.74. Just to talk about math real quick, I do this in tons of channel classes, so I'm sure you've heard this before. If you had me, I know a lot of folks have been here before. If you ever get a fraction like this and need to solve for it, the fast way to do math on the MCAT is to multiply your numbers by some number that turns the bottom of your fraction into just either 10, 100, or 1,000, something with just ones and zeros. So if you multiply them both by 2, that turns it into 100, turns the top into 74. That makes it easier to say, oh yeah, that decimal is 0.74. So just in case if you aren't good with decimals, I highly recommend multiplying by something to turn it into a decimal for you because we don't have calculators on test day. Cool. Yeah, it just makes it faster, Emma. So yeah, perfect. See, I was not sure everyone knew it. So that's my favorite math trick. I agree. I do that all the time because I'm not good with fractions. I have to turn everything into decimals to think about it, to be honest. And I know a lot of us kind of think that way too. So, but if you're good with fractions, work with the fractions, that's totally fine too. All right, so the other one down here is RF value of 0.33 because it's 22. So once again, 22 divided by 50, same thing as 44 divided by 100, hence 0.44. So then that means sample 2 is more what? This guy right here. What would its property be relatively? It's more polar. You got it. That's what this is really all about. And so now that we've covered this, we're going to go through the rest of the chromatography very quickly. It's all the exact same idea. You've got a mobile phase, you've got a stationary phase. The more the sample likes the mobile phase, the faster it moves. The more it likes the stationary phase, the slower it moves. And so column is a classic example of this. There's different types of column. The example we're giving you here is a pretty common one where we use the same thing, but in this case, well, actually, no, same thing. We've got a polar silica stationary phase, and we've got some kind of nonpolar solvent or mobile phase. So we put our sample in the top, and then we, of course, dump our mobile phase through, and then these will elute at different times. So whatever is more nonpolar elutes first, because once again, if it likes the mobile phase, it moves faster. If it likes the polar stationary phase, It just comes out more slowly. So it's the same, it literally is the same thing as we saw in the first one. Mobile phase stuff moves fast, stationary phase stuff moves slow. Let's do size exclusion though, because I think it was Hannah brought this one up. Gabriella brought it up actually. So size exclusion. So the way that size exclusion works, because this does show up once in a while, is a little bit counterintuitive. But so what we do is we fill this column with a bunch of beads. And what do we know about these beads? What do they have in them that makes them special? Hannah, that's a possible problem. Generally, that's what you use high pressure liquid chromatography for. You force it out. You basically apply pressure at the top. But it is definitely something to worry about. You got it. So yeah, you guys got it. These beads have tiny little pores in them. And so they've got these tiny little pores and channels dug throughout the entire thing. So what happens is anything that is big basically can't fit into the pores. It goes blink, blink, blink between the beads and comes right out the bottom. So big stuff just blinks right through, pops out the bottom. It goes fast. Yeah, big stuff moves quickly. Small stuff, I'll label this one as small, it goes through the bead and it gets kind of stuck in the thing, and then it goes to the next bead and it moves around the thing, and then it goes to the next bead and it kind of loops through the tunnels. And it just ends up taking longer because it gets caught in all these little beads and kind of weaves its way through and then finally pops out the bottom. It's lingering, Laura. That's a great way to say it. So this is kind of weird because it's the opposite of what works in electrophoresis, where in electrophoresis, small stuff moves quickly, big stuff moves slowly. Size exclusion chromatography is the exact opposite because it's a totally different setup. The big stuff can't even fit in the beads, which is why it goes fast. Cool. There we go. There we go. I like it. The more you can think of examples and metaphors, the better. The better. All right, so we're going to go through the rest of these pretty quickly. As I said, this is just general ideas that they're all the same idea. You once again have a mobile phase. You've got a nonpolar. You got a mobile phase and a stationary phase. Now what you do is you basically have an oven that heats it. Why would heat be important here? Why is heat important? Yeah, it's gas chromatography, right? So you got to vaporize it. So it needs to be vaporized into a gas, so we'll usually apply heat so we can actually have it in the gaseous state. All you do then is inject your sample into the injection port, gets vaporized, and now in this case, though, these coiled wires are the stationary phase, right? So the coiled wires are the stationary phase, and the actual gas that it's injecting it into would be the mobile phase. So as it moves through this piping, the more it likes the stationary phase, the more it gets kind of stuck in there and comes out more slowly. And so then this hits the detector and you get different spikes according to different times that everything elutes. But it's the same idea. If it likes the stationary phase, it takes longer to elute. If it likes the mobile phase, it elutes faster. In this case, you just need some kind of fancy computer to tell you what it means. But it's the same general idea. I don't know, Hannah. That's a good question. I don't know if you call it a super loop. I've actually never worked with one of these ever before. I just know that they're expensive and fancy and that it reads it out to a computer. But I do know it is coiled wires. They all have basically coiled tubing, and that's what the stationary phase is. But we'll ask Rohini. We'll see if she knows. It looks like a solenoid, Brandon. That is true. It does look like a solenoid. I'm not going to speak to it though. I have no personal experience with them. I just know that it's the same idea. But yeah, the thing is, the MCAT's not going to make you know it. It's more like if you work in an Oracle lab and actually use them, you'll probably know more of the details. But yeah, most of the stuff, the whole idea of giving you these other examples is to show you that it's other examples of the same concept, and it's the concept that matters most. But that does look like a solenoid. I agree with that. Cool. All right, so HPLC, high performance liquid chromatography. See, Matt, I knew someone knew it. Someone's worked with this stuff before. But so it uses, once again, like really, it's the thing you need to know for the MCAT. So you got stationary phases, you got liquid phases, right? You're going to do this under high pressure. You force it through the system. One thing that I would want you guys to know, though, about high performance liquid chromatography in terms of applications, we generally use this if you have a very small sample size, and it's exactly what we talked about before, how you might be nervous that you'll get a little bit of your sample actually stuck. Hannah brought this up a little bit ago. Inside the column, right? And so if you've got a small sample and you're really nervous about it, you can use HPLC to kind of force it through and get your data that way. Maybe. I mean, you wouldn't have many of them, Hannah, so that would make sense. Like if you had special proteins that you've kind of like mass produced and then have a bunch of. I imagine proteins would work here. They definitely wouldn't work for gas chromatography. It'd be too big. But for HPLC, I think it would work pretty fine. But yeah, small sample or expensive sample where you're kind of nervous about it. And then basically it's an automatic system once again. You've got this fancy computer. Yeah, exactly. Oh, interesting. I know they used to call it high pressure liquid chromatography. Now they call it high performance liquid chromatography. So they swapped out the pressure for performance. But that was traditionally, it was just called high pressure. I didn't know that they're doing low pressure now. That's even fancier though. But exactly. Okay, there we go. There you go. I like it. Exactly. I've only got 2 drops of it, and so I can't waste it. I need to use this technique. That's a good way to think about it. Perfect. There we go. Matt's got the details on the spec stuff. So HPLC would purify peptids. HPLC for full proteins. I guess that's exactly. So HPLC would just be for little peptide chunks. If you want a full protein, that'd be the FPLC. Cool. Which is outside the scope of the MCAT, so we don't need to worry about it. All right. So main thing to be aware of here is the general themes. Polar versus nonpolar, stationary versus mobile. Honestly, the way the MCAT tests most of this stuff is not the specific details, it's more the general ideas and the themes, and most importantly, how this relates to the other science topics, which in this case is primarily Gen Chem. So this is a good example of how you'd actually see this stuff tested. Let's bust out a poll. We have one around here somewhere, right? Liz, do you know where it went? If you want to grab it and just bring it on screen, we can bring it up for everybody. I think we lost it. There it is. Sweet, thanks much. I'll clear it out. All right, so throw your answers into the poll as soon as you got an answer to give. This is a classic style question on the MCAT where you can actually answer this question without even reading the question. So we know we're talking about RF values. And so if you got it, Mary knows the rule. So if we're talking about RF values, we're talking about things that are either polar or nonpolar. And so even if we don't know if we're looking for something polar or nonpolar, all we got to do is find which of these is not like the other. Exactly. Hannah knows the Sesame Street rule. It seriously works a bunch for the MCAT. It's kind of surprising, though. So pentane, polar or nonpolar? Nonpolar for sure. How about toluene? Do you guys know toluene? It is also nonpolar. What is toluene? It's a good one to know for the MCAT. I guess I could draw it. My pen tool's working, so I might as well. So toluene is a fancy version of benzene plus a methyl group. Exactly true. So benzene, answer choice D, would be that. Toluene is just that with a little methyl group sticking off the side. I do recommend knowing a couple of your other common benzene ring form like compounds. Like this would be toluene. This would be, excuse me, what? Phenol, exactly. The one with nitrogen is another common one. What's this guy called? NH2. Ooh, I don't know this one. Close. It's aniline. You guys heard that one before? There we go. Yeah, Valerie's got it spelled right there. Perfect. Yeah, so that's aniline. Mostly phenol and toluene. Those are the big ones that you definitely need to know. Cool. Got it. All right, so, but do be aware of those certain common names. The most important common name of all, though, is probably acetone and acetic acid. And here's a good example, ethyl acetate. Once again, acet, ACET means 2-carbon root. If it ends in 8, though, what are we talking about here? Specifically, it means it's actually a conjugate base. So you know how, yeah, exactly, there you go, it's an actual anion. And so be aware, whenever we have actually ic acids, actually, let me give you a little shortcut rule here. Exactly, it's a carboxylic acid derivative. If you ever have an ic acid, always turns into 8 anions. So any of your ic acid turns into 8 anions, where any of your us acids turn into your 8 ions. So basically, all you need to know from this is that it has a charge. You're like, oh, it ends in 8, it's going to be a charge, which of course means that it's more polar, so it is going to be the correct answer. It's just the only one that's different than the others. And so regardless if you know whether you're looking for something polar or something non-polar, really, well, that actually shows ethyl, that'd be ethyl ethanoate. So same idea, though. It's first time we ran through, so yeah, I would say it should be CO minus, Jessica. This would be, I want to give you the proper name. That's ethyl ethanoate. That'd be ethyl ethanoate. That's what is that compound called? That is the proper name for it. It might be called also, sometimes they use acetate actually as common language too, where it doesn't necessarily mean the conjugate base pair. It might just be another common name for the same compound, but that's your full actual IUPAC there is ethyl ethanoate of that thing. It's an ester, you got it. So it's an ester, but no matter what, of course, it's going to be more polar. It's got oxygens, none of the other things have oxygens. So regardless, we know that's right because D and B and A are all going to be way too polar, non-polar, excuse me. Oh, great question, Hannah. I can draw that since we're here. So this is an ester that we have on screen. An ether is when you just have a normal oxygen in the middle of a carbon chain. So this would be diethyl ether, whereas this would be your ester right here. Yeah, it looks. I like to think of it as a bat. I think that diethyl ether is like the bat wing flying at you. There we go. See, Hannah's drew a picture for you. Perfect. All right. All right, so that was the first thing, all of our spec stuff. We got two more, I think, after this to talk about. Let's talk about separation techniques. So separation techniques, first two big ones we'll talk about are distillation as well as, this would just be separatory funnel, what do we call it? Extraction. So this is extraction. So you have a separatory funnel with two different liquids. So we've got this yellow liquid on top and this blue liquid on the bottom. We generally use acid-base stuff here. That is completely correct, Hannah. That's how we generally extract stuff. Which one is on top, the organic or the aqueous layer? It's a trick question. You don't know. Unless they give you data, exactly, Lauren, we don't actually know. All we know is it's higher or lower in density. It is less dense, exactly true. So the top layer is going to be less dense, the bottom layer is going to be more dense. Generally speaking, though, organic layers tend to have lower density than aqueous layers because water is pretty darn dense and oil floats on top of water. So if it's a standard oil, it will be less dense, but just for the MCAT, it'd be an easy way for them to trick you. Like, if they give you density values, you got to use the density values first and foremost across the board. All right, so what we do with these, generally speaking, is you put your compound in, like, let's say you've got a mixture of, you somehow mixed up your superpolar thing with your nonpolar thing, so you add it to the separatory funnel, you shake the crap out of it, all your polar stuff migrates to the polar region, all your nonpolar stuff migrates to the nonpolar region, and then when you pull the little stop valve here, notice whatever's more dense comes out first, it drains, and you can separate the two. Yeah, exactly. It's exactly, Hannah, right? So it's like your, is it Italian dressing? Yeah, I think Italian dressing is that, right? It's oil and vinegar. You shake the crap out of it, but after a little while, it's going to actually separate out. You got it. Yeah, you salad dress it. That's a great way to say it. All right, so this one is organic phase, nonpolar molecules. As we said, generally speaking, it's on top, but reality, right, you got to look at the density to be specific. Aqueous, of course, is on the bottom, or very polar molecules. So generally speaking here, though, Hannah brought this up a little bit ago. We often deal with extraction when it comes to acid-basic properties. So for example, if let's say we have a solution of like carboxylic acid and an alcohol. So let me give you specifically though, if I want to draw this carboxylic acid, why would I make a point to make it benzoic acid and not just like ethanoic acid or something like that? How would benzoic acid behave differently in solution than good old-fashioned ethanoic acid? Yeah, what does that aromatic thing do to it? It is acidic. It's more acidic for sure, Brandon. It's also kind of polar, but would it be in the organic or aqueous layer? As is. As is drawn, it would actually be in the organic layer. This is also a good thing to keep in mind when test day comes up pretty soon. Whenever you talk about your amino acids, right? Amino acids, that's got a carboxy group and an amino group. But if you've got an amino acid that actually is a aromatic amino acid, where do aromatic amino acids tend to be in terms of protein structure? Just like this guy's also aromatic. Inside, you got it. So if it's got aromatic rings, that aromatic ring is such a large chunk of the molecule that it's basically going to overcompensate for the carboxylic end on it. And so it will be hydrophobic. This will be in the organic layer. But if you want to make it move into the aqueous layer, what would kind of incite this giant thing to move into the aqueous layer? You got it, deprotonate it, right? So add some sodium bicarbonate. Sodium bicarbonate's a fairly weak base, right? But carboxylic acid's a fairly strong acid, especially if it's benzoic acid, right? As we said, this is even more acidic because it can resonance stabilize itself. And so if you add a weak base is going to plop off that protein. Pluck off that protein probably makes more sense. So pluck off that protein and leave behind a negative charge. Oh yeah, sorry, protons. Yeah, I'm messing everything up. So it plucks off that proton, which then leaves a negative charge, which then resonates between both those oxygens as well as the whole aromatic ring there. Jeez, I'm running out of steam here. All right, you guys got it though. So that's the cool thing. If you ever add a weak base, it's really good at basically pulling off protons from things that are fairly acidic. Whereas if we had something less acidic that was similar in structure, like we'll pretend this is a phenol, right? Phenol would not get deprotonated by a guy like sodium bicarb. It's also aromatic, and yes, it can resonance stabilize a negative charge, but it's just not as acidic as a carboxylic acid, so ain't got a chance right there. All right, so that's the way we often use extraction. It's taking advantage of the acidic or basic properties of things. You add the right solvent, so you can actually, there we go, it's already on the screen, give you, of course, the deprotonated version of it there. Oh, and also, just as a backup for everybody, you need to be aware of this. If you ever see sodium on the MCAT, sodium means jack. All it means is that if it has a positive charge, this whole thing here has a negative charge. Exactly, it's irrelevant. It's a spectator SAR. Exactly, we talked about that yesterday. But so remember, sodium, spectator, don't care, but it does mean there's a negative charge next to it. So it's the negative charge that we care about, not the sodium that we care about. Cool. I like it. All right, so this guy would be aqueous, as we said. The other one would be organic. All right, so bases, on the other hand, can be extracted with strong acids. Why would you want to use a strong acid to extract a base? What would that make sure of? It's going to definitely give that thing a positive charge. You got it. So it's a more surefire way here. Generally, like speaking, you don't really have super strong aromatic bases as much, but like we do have like benzoic acid is a classic thing that you'll see right there. And so yeah, when you add an acid to it, when you give a strong acid, it's definitely going to protonate this guy. Once you protonate this thing, it'll definitely give it a positive charge, which means then it will also move into the aqueous layer, as you can see there. I'm gonna clear all this out just so if you guys do want to take a screenshot. It's a pretty slide with a bunch of info on it, so you can kind of keep that for later if you like that kind of stuff. There we go. And Rohini's got a bunch of stuff for you in the chat about specifics on that. Pretty much, you got it. So like either adding acid or base, it just depends on what you have. So sometimes we'll see passages where you add an acid, and then you extract something, then you add a base, and you extract something. Given the order of operations, like if it extracts the base, it means your thing was slightly acidic. If it extracts with an acid, it means your thing was basic. If that makes sense, Hannah. So it's kind of like it'll extract the opposite because it gives the other thing a charge. And I think we do have a question later today that basically makes us do that, where it kind of goes through an order of operations of adding acid then base and figuring out what was left behind. But as with all things on the MCAT, there's probably a shorter, quicker way than actually doing the full analysis, which is, I think, the thing we do today, too. All right. Distillation is the next way to separate liquids. What does distillation separate according to? Boiling point, perfect. Yeah, so the whole thing with distillation is that it separates according to boiling point. Whatever has a lower boiling point boils off first. And so if you compare water and ethanol, what has a lower boiling point? Ethanol, exactly. So this is how we make booze, right? So the whole idea is you take a bunch of actually, if you want, you can make liquor out of beer or wine. It's actually kind of interesting, but there's a bunch of new like whiskeys I've heard where they're actually distilling beer to make whiskey out of it, which I thought was kind of creative, but it's the new rage. Also illegal, as Christopher says. But so the whole idea is you have a mixture where it's partially alcohol, partially other stuff, and as you boil it, whatever has a lower boiling point boils off first, and then it condenses in this tube, and then it drips out, and you get your pure distillate. But yeah, as Christopher says, about 70 degrees Celsius is pretty close for ethanol. Less than 100 is really what matters most. Cool, perfect. There we go. See, exactly. The more you can apply to the real world, the better. So that's just the standard distillation, right? Whatever's a lower boiling point boils first. You then consolidate it and then keep it. It's also why alcohol is also known as spirits. The reason that it's called spirits is because back in the day when you boiled it, it made this weird vapor, which created this, alcoholic mixture. And they were like, oh, it must have gotten the spirits into it or some ghost stuff, like that. But you got it. And it's also why you can cook with wine ester, because if you cook with alcohol, it actually boils the alcohol off so there isn't any alcohol left in the food. And so it leaves behind the more flavor parts of it, not necessarily the actual alcoholic. And so even like kids' food, sometimes they'll cook it with like, alcohols because it just boils off regardless. Cool. Yeah, right? There we go. Well, lower boiling point compounds are boiled off first. There you go, fondue. Exactly. You gotta make sure you heat it up enough. There we go. Yeah, vodka sauce. Totally true, Brandon. That's another good example. Because it is an actual type of sauce, which I imagine it just boils off when they make it. But I don't really know how vodka sauce is made, so I don't know for sure. All right, so now this one's a little bit different. What type? Oh, actually, it says on the screen. So it says fractional distillation, but how is fractional distillation different? Awesome. Oh, interesting. I didn't know. I never get vodka sauce. I didn't know what it was. Yeah, we got a wiggly tube. It causes the surface area to go up, which, what is the net effect? Jennifer says close boiling points, totally agree. Yeah, if you got to separate out close boiling points, Brandon and Jennifer kind of tying the same thing. Sarah's got the same thing there. Perfect. So if you got a bunch of compounds with similar boiling points, by doing fractional distillation, what really happens, I'll kind of draw it out for a sec, but you boil this up and then it consolidates. And then once the heat rises, it boils again and then recondenses again and then boils again and recondenses again, and you're just able to more fine-tune the differences. Yeah, it's for picky separations. And if you went to a state school for college, as I did, instead of giving us fancy fractional tubes, anyone go to a state school where they didn't give you a fancy fractional tube? What'd they give you instead? I always laughed at this. You can usually tell how well of funding your school has by steel wool, you got it. So generally speaking, they'll just give you steel wool and have you cram your normal distillation tube full of steel wool, which does the same thing. It's still increasing the surface area. It's just not as pretty as an actual fractional distillation tube. So yeah, exactly. Even at UC schools, here we go. It still works. Still works perfectly fine. It's a good way, though, to get the gist of how well the OChem lab is funded, which doesn't say anything about the quality of the school. It does tell you, though, about the funding of at least the science departments. So cool. Totally works. Surface area is definitely the key word there. Generally speaking, for the MCAT, do you guys know what the boiling point difference is for fractional distillation that you want to have down? It's approximately about 25. Perfect. You guys know it. Perfect. So yeah, if it's about 25 degrees apart or less, you want to use fractional distillation. If it's more than 25 degrees apart, you can use good old-fashioned simple distillation. So generally speaking, distilling alcohol and water right apart, you could just use simple and it should be fine. Cool. Oh, one other type. What's the one other type of distillation that we don't cover in this slide, but is good to know for the test? Yeah, we don't cover in this slide. Nice. Vacuum distillation is the other. When do you use vacuum distillation? Is the third type. You got it. So when your boiling points are really high, use vacuum distillation. I've actually heard 150 and 125. I don't really know what the norm is, but I've heard both of those numbers before. But pretty much if you've got a significantly high boiling point, you want to use vacuum distillation. What that effectively does is what? There you go. Decreases atmospheric pressure, which then, of course, allows it to boil at a lower point. It's kind of like how here not really in Denver, but like up if you go really up in the mountains. For example, I think if you go up to the top of Mount Everest, water boils at about 70 degrees Celsius. Because it's such thin atmosphere and so low atmospheric pressure, it actually boils really, really, really easily. And so you got a lower atmospheric pressure, the lower boiling points are going to be. Yeah, I think I remember looking it up once, but I think it's about 70 degrees on Everest. Also covered dead bodies. I'm going to think about that for a second. Am I really getting out there? Yeah, it's the opposite of a pressure cooker. Cool, yeah. Denver's hip right now. Everyone's moving here. It's funny. It's fun. Cool. But yeah, I'm not sure what you're getting at there, but there we go. You guys got the main points. Let's clear this out. Oh yes, Everest is covered in dead bodies. That is totally correct. We should talk. I want to see who your teacher is because I have a bunch of friends teaching in Denver. But let's solve this question first, and we will move on to the next concept. Also, there is a typo on this. I noticed before class. I just want to make sure we're on the same page. Yeah, Mary, that's exactly it. It's Z. It's supposed to say Z here, not Y. That's a slight typo. Thanks, Zach. All right, that should clear it up, though. I was confused when I was prepping this, and I realized that's just a typo. So it is compound Z. Looking pretty good. So after this, all we do is electrophoresis and then IR and NMR. That's the content for the day. We got most people voting, looking pretty solid. So compound Z is in the middle. So if we're doing fractional distillation, well, it's middle in terms of the boiling point, right? So what's going to boil first? What would come off in fractions 1 through 3? Gotcha. Diethyl ether, yeah, so diethyl ether will definitely be part in fractions 1 through 3. Then the second thing, 55 degrees Celsius, would be in the next set of fractions boiling off. And then the highest boiling point will boil off last, which would be ethyl acetate once again, using the common name that I got a little bit worked around with, but it's the common name for that thing, will be fractions 8 through 10. Remember the proper name would be ethyl ethanoate if you want to use the proper language. But of course, we do see acetate quite a bit, and they do use common language on the MCAT too. But you guys got it. We have about 90% going for answer choice B. You guys are spot on. Definitely answer choice B. Cool. All right, let's move on towards our third to last topic for the day. Oh man, I haven't made a star in a while. I'll figure out how to. The tools have changed since then, Hannah. I have to refigure out how to build them. So we'll do electrophoresis. It's true, we actually have new drawing tools. It's all different. It changed recently. But let's run through electrophoresis, and I'll figure that out for you while you guys are doing the next problem. So first things first, electrophoresis, what type of cell is this, electrolytic or galvanic? That'll be our first step. Oh, I'm moving on to Gen Chem. We're going past this stuff. This is an electrolytic cell. What does that mean about the delta G? Electrolytic cell. Thus your delta G is positive. So delta G is greater than 0. Also means that it's non-spontaneous, right? So that means the exact same thing. Oh, actually, that's got to write on the top of the skull. Perfect. It's already written there. There we go. So it's electrolytic, delta G is positive, E of the cell, of course, is going to be negative then. Non-spontaneous, that's a thing to keep in mind as well. So what charge does the anode have, positive or negative, if it's an electrolytic cell? Anode would have a positive charge. This is the trick most people fall into. So in galvanic cells, anodes are negative and cathodes are positive. But in electrolytic cells, we're driving a non-spontaneous reaction, so it actually switches the sign because you're making a reaction occur that wouldn't naturally occur. Yeah, Mary's got a great point there. These batteries right here, those are galvanic cells. That's totally true. Any kind of battery that creates its own energy, remember galvanic and voltaic means the same thing too. The process that it's driving here, so you're using a galvanic cell to create an electrolytic cell between this page right here, if that makes sense. But so you got it, yeah. So the generally speaking thing is that galvanic cells would be discharging a battery, right? It's using energy, whereas electrolytic cells are either charging a battery, which happens when you plug your phone into the wall, or it's running processes like electrophoresis. Yeah, to run the Q&A, Hannah, it's a little bit of a wormhole to get too specific, but we can talk with it more. But yeah, I mean, you could say that because I'm not going to get into it. I guess it matters what your perspective is, but I like what you're saying. But so generally speaking, anode positive, cathode negative, which means which side's DNA going to migrate towards if we did DNA here? It's going to migrate towards the anode, the positive, because of what? Why will DNA migrate towards the anode if we had DNA? Because of that sugar phosphate backbone, you got it. So DNA all has a negative charge, and so that's why when we separate DNA, since it has a certain charge to mass ratio, we pretty much are just separating it out according to mass or size. The bigger the piece of DNA, does it move faster or slower? The bigger the piece of DNA is. Slower, yeah. The bigger the DNA, the slower it is. The smaller the DNA, the faster it is. And what do we generally expose our DNA to before putting it in these so we can actually look at different chunks of DNA? It's a certain type of enzyme. Well, the detergent denatures it. That's true. So yeah, I agree. Often you'll denature it and kind of everything worse. But yeah, restriction enzymes. So remember, restriction enzymes are specific enzymes that actually chop DNA at specific regions. And so you basically chop it up into little chunks, and then you electrophoresis it, and you can look at different people's DNA and compare how different they are because it'll all get chopped up a little bit differently. Exactly. So you got it. You wouldn't want to use an entire piece of DNA because it'd just be one thing moving across. So generally we use restriction enzymes to chop it up a little bit first. Cool. So notice cations migrate towards the cathode, Anions migrate towards the anode. You can use that little rhyming mnemonic as well. If you use proteases though, Hannah, you would have to be using not we use SDS for that, right? But you could use it for proteases if you were doing an analysis of peptides. Trips, yeah, because trypsin chops at specific amino acid points, right? And so you could totally use specific ones too. That's true. Just not for DNA, right? That would be for peptides. That'd be the big difference. But yeah, trypsin, chymotrypsin, all cut at specific regions. Totally true. Cool. Specifically, I don't know if you guys remember this. Do you know where trypsin cuts at? We can get deep here for a second if you want, because this is why it would work. Nice, nice. Lysine arginine, you got it. It's aromatic's not trypsin, it's the other one. Which one's aromatic? It's basic for trypsin. Other one that sounds like it. Chymotrypsin cuts the aromatic ones. There you go. So yeah, chymotrypsin cuts the aromatic. I've heard before, actually a student of mine last night said this. They remember chymotrypsin because it has the O, like aromatic rings, right, for chymotrypsin. And then trypsin, of course, would be the lysine arginine. That's questionable, Valerie. You know, it's hard to say whether it would be passage-based or if it would be straight up, you know, like you need to memorize it. But I'm actually not sure. The old MCAT, definitely no. New MCAT, borderline, super borderline, hard to say. So that's why. If it's in the review notes, generally speaking, I would trust it because remember, we base the review notes solely on the list from the AMC, so I'd have to double-check the list itself. But if it's in the books, I would know it. There we go. And Rohini's got the breakdown for you. So cool. And you all know the site, the AMC's actual page that has the full list cred of Kapte. Have you looked at that before? It's a good thing to be aware of and to check out if you haven't. The books were all based on it, so you don't really need to, but it's a nice thing to be aware of and to actually kind of like see it with your own eyes. But do be aware all of our 2015 material is based on that list from the AMC. All right, cool. So let's talk about polyacrylamide gel electrophoresis. We deal with this not so much with DNA, but with our proteins, which we were talking about a second ago. So we often use proteins for these. Two things that I want to talk about is we make these different columns here. You've got your basically molecular mass marker there, and then have your different things where same thing. The larger mass moves more slowly, doesn't go as far. The smaller mass goes a whole lot faster. So same idea. Main idea is you can use electrophoresis for proteins. You can use it for amino acids. Well, sorry, for proteins or peptides. You can use it for DNA as well. You can use it for other stuff too. But so be aware when it comes to the protein stuff. For SDS page is when we separate according to mass only. That's because SDS is a detergent that basically covers the entire thing with a negative charge. So basically it makes all of your amino acids have negative charges on them, so it functions pretty much the same as DNA electrophoresis. So SDS page turns proteins effectively into like DNA. Native page doesn't change the charge, so it separates according to mass and charge. Cool. All right. That's the main thing to know in terms of electrophoresis. Let's do a question on it, and then we'll cover our last topic for the day. Clearing out the answers. Throw them in when you're ready. Or I guess last two topics. We'll do IR and NMR. That looks like most people already answered. Nice work. So since they label it A, B, C, D at the top, that means this is basically our wells, I believe is what you, yeah, wells is what we call them. And so it means everything's kind of moving down. So if we're doing nucleic acids, what do you think about A? If we're doing, notice, nucleic acid fragments. More positively charged than that. Nope, we don't know that because remember, DNA is all negative. You got it. So A is an incorrect answer choice. That's not going to work. We don't have many votes for B because we can't tell if it's RNA or not, right? You're not going to be able to figure out that kind of information from just looking at the slide here. So we're talking more about size. And notice C and D do address the right issue of either larger or smaller than. That's what we want. So the stuff at the bottom, like D, is that going to be the biggest or the smallest? You got it. It's going to be the smallest, which is why we have over 90% going for answer choice C. And I heard a rumor has it that when people answer over 90, these weird stars start appearing on the screen. I don't know where they come from. As you can see, I'm not even touching the monitor or anything. But they still appear. Weird, right? Don't know how it happens. Black Star of Doom. I didn't do it. I told you. I'm not even touching the keyboard. I can't do it. It's happened on its own. It's magic. All right, so there we go. We talked about the size, the difference. As you can see, I'm just going to fill in all this stuff. You saw it. But exactly, right. The small stuff moves a long ways. Big stuff barely moves at all. And Rohini's got the recap. All right, so last thing we do today is talk about NMR and IR. So the thing first that I want to talk about is just what this stuff looks at. And so let's start off by talking about IR spectroscopy. And so infrared photons can be absorbed by polar bonds, which causes a vibration, a stretch, rotation. Basically, it's any kind of movement, like twisting, torquing, moving, bending, weaving, bobbing, all that kind of stuff. And it's that combination of different movements, and we'll show you a couple right here. Whoa, 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 whoa. That would be an example of symmetrical movement. Isn't that sweet little dances there, Hannah? Or we could do, of course, an asymmetrical movement over here. Whom, whum, 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 whum. Also happens. Or we could talk about a different type of symmetrical movement here, where it does probably this one, I'm guessing. Yep, exactly. It does the bending and the weaving and the bobbing. I think the twerking was the second one, Matt. I think twerking was the second one. And then the last one is another example of a symmetric stretch. This is just for fun to show you that it can happen lots of different ways. But so you don't need to know all the different types of stretches, but you do need to know that when infrared light hits these bonds, it causes them to move, and it's the way that they move basically gives off certain type of vibration that we can register and then actually tell what type of molecule it is. And so if there's one thing to be aware of, since specific bonds give specific IR signals, what are these actually telling you? It's identifying specific, true, but like types of bonds, which what will that give you a hint of? Yeah, functional groups, right, Christopher? Exactly. So like using this, you're like, oh, well, it's got a CO bond that's double, so it's got some kind of carbonyl functionality. You got it. So the downfield thing is, we talk about that more so when it comes to NMR. But for IR, this is generally more, well, I guess you could do both. It's true. I guess we use the field in both. But it generally tells you types of functional groups. That's the big take-home. So there is one thing that you need for the MCAT to identify from this IR spec data. There's actually only two you need to know for sure. One of them is here, and it is exactly, Mary's got two of them, and Hannah's pointing it out and already named it. It is this thing right here. It is a broad peak around 3,300 or so. That is your alcohol. So everything down here doesn't matter. It's the fingerprint region. You're not going to be quizzed on it on the MCAT. And there really is just two that you need to be aware of. And that's, of course, your alcohol peak right there, as you can see it. And then your, what's the other one? It's actually not here, so we don't have it. We have a blue dot where it would be. I can draw it in. That'd be carbonyl. So if you have a spike right around 1700, the blue dot's where it would be. That means that you've got carbonyl functionality. So what kind of compounds would contain that bond? That C-double-O bond. Carboxylic acid, aldehydes, ketones, anhydrides, esters, amides, acyl. You could go on. There's a lot of them, but exactly. All of the things that have carbonyls would all have that. Nice. One big list there. All right, so honestly, that's it for IR. That's all you need to know for the MCAT. So memorize, of course, that it's infrared, the reason that causes it, the bonding and the bending and the twerking. But no alcohol is broad peak around 3,300 once again, and carbonyl peak is a sharp peak around 1,700. If you know those two things, you'll be fine for IR for the MCAT. I know that's all we're going to talk about today. That's all you need to know. So we'll spend the last part of class talking about NMR. Yeah, seriously, right? Because there's a bunch. I know in college I had to learn a bunch of little things, but not for the MCAT. And also remember, they're doing less straight OChem now these days. So like the OChem you do get usually is going to relate back to like probably amino acids or something. Like, oh, it's got a carbonyl peak, so it's probably an amino acid, kind of stuff like that. So it probably will loop back to something that's more biochem based if you see it on the test. That's really what the AMC loves, is connecting the dots between the topics. All right, so last thing is going to be NMR spec. Takes a little bit longer than the last one, but so be aware. Nucleon with that odd number of, error, it is not protons. As I said, this is our first time running this class. We will fix that next. What should that say instead of protons? Because it doesn't need an odd number of protons. Not electrons either. It's actually an odd number of nucleons. So an odd number of nucleons, not protons. I know H1NMR works perfectly, but there's another type that actually doesn't just have an odd number of protons. It's got an even number of protons, but an odd number of nucleons. Carbon what, Valerie? Carbon 13 mark. Matt, exactly, you got it. Yeah, so carbon 13's got 6 protons, 7 neutrons. And so a nucleon is either a proton or a neutron. It's just the parts of the nucleus, Mary. Sorry, it's a weird term. But so yeah, nucleon is either proton or neutron. It's a fancy term for both of them together. And so carbon 13's got 13 total, bundles in the nucleus, so it works too. Exactly, perfect. All right, so they've got magnetic moments. And so if you align them in a magnetic field, they'll spin to align with that applied field. And so then we can basically take information from that spin and figure out exactly what type of protons they have, or if we're doing carbon 13, what type of carbon they're composed of too. For the MCAT, you are far, 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 far more likely to see H-NMR, H1 NMR specifically, than you are to see carbon NMR. It's been maybe once or twice in the history I've heard that, or I don't know if that's once or twice, I actually don't know. But it used to be on the list, but just didn't really ever get tested. But proton NMR, big time, huge. All right, so radio source there, basically we send a radio signal at it, it causes them to move, and then the way that they move back and realign with the field, that's how we basically get all this data. So let's just focus on doing how to interpret this. This will be the kind of last part of class. So what we're looking at when we use HNMR is we look for different types of protons. So how many different types of protons do we have in this molecule? Or, yeah, hydrogens, you got it. Same idea, though. We got 3 different types of protons. You got it. So we've got, of course, this guy right here. These are all chemically equivalent protons. We've got these kinds of protons and those kinds of protons. So we've got 3 different categories of protons. So that's the first thing. Now, what determines the height? Oh, actually, this looks weird. Oh, no, it's not. It's good. Sorry. The number of protons. So the height is determined by the number of protons. You guys getting a lot of other things there. That'll be other things. We'll hit all of those points in a second. So how tall it is determines the number of protons. Now, why is C taller than A, even though we have the same number of protons there? Exactly. C is not splitting, whereas A is splitting. So let's talk about 2 main things. And so the first thing is the height is determined by the number of protons. The second thing to be aware of is that the further downfield something is, further to the left is downfield. Downfield means more de-shielded. So downfield means more de-shielded. And so more de-shielded means more electron withdrawn, effectively. So which group here is the most electron withdrawn? You got a B guy there. So notice B is the furthest downfield because not only is it still pretty close to this guy, it's bound to an oxygen as well that's in the middle of the chain. So he's going to be the most withdrawn. There's only 2 protons there. It's got some density basically sucked away from him there. So what are a couple peaks that you want to definitely memorize? I'm going to draw some more real quick just in terms of this downfield idea. Yeah, this is a weirder example, Gabriella. I want to do some more straightforward ones because this one's actually a little bit tricky. Aldehyde's a massive one. So aldehyde's closer to like 9.8. And here's my breakdown for you in general. Anything that's sp2 hybridized is way far downfield. So for example, if you have aromatic stuff, aromatic hydrogens, they're like 6 to 8, right? Aldehyde, 9.8, super far downfield. And so I'm going to do big picture here. We have a bunch more examples we can talk about in Q&A after class. But so the more downfield it is, the more electron withdrawn it is. That's the key second step. We said the first step was the taller it was, the more protons. The third step is splitting, and this is what you guys already brought in. So the splitting thing that happens here, all you do is you look at your hydrogens and you count the number of neighbor protons. Notice that C doesn't have any neighbor protons. There's no protons here. So that ends up as a singlet. It's not splitting at all. If you look at A here, how many neighbors does A have? 2. So this is the n+1 or the neighbors plus 1 rule. So that's why A appears as a triplet. As you can see, it's got these 3 different peaks there. And when you look at B, B appears as a what? Because it's got 3 neighbors now. A quartet, exactly. So that appears as a quartet. So all you do is you look at the neighbor carbon and you add up all of the protons on the neighbor carbon. And that's how you get your final thing right there. Exactly. Yeah, sometimes you do call those multiplets is the way that we'll see them. If they're split a whole bunch, they don't even bother calling it a whatever thing. They'll just call it a multiplet across. Cool. So there we go. We talked about the size. We talked about the more electronegative ones, right? The further it is to the left, the more downfield it is, and the more neighbors we have, the more coupled it is, and the more deshielded it is. Cool. If you guys want to take a screenshot, this is basically a summary of all the stuff that we talked about. Actually, that's the last slide before the homework passage. But feel free to snag a little screenshot of that. If you guys want to talk shop about other examples, let us know. We can talk about it more. But the key is those three things. Keep it in mind. Number of protons is the height. Downfield to the left is how withdrawn. And then neighbors plus 1, that's your splitting, that's your coupling. But that's about it. Cool beans. All right, so let us know if you have questions. We can hang out and answer them. In the meantime, as Rohini says, Nzinga's on next for some Psych and Soch. So stick around. We'll see you soon, and have a fantastic rest of your evenings. Adios, everybody.